Hi, I'm Stevie C and the place to be. In this video, I'll be diagnosing and hopefully repairing an LED disco light. I was given a pair of these RGB PARcan style lights to repair, so I thought I'd walk you through how I went about it. The information given by the client was that the light simply stopped working one day and it blew the fuse in the plug. This told me it was probably something in the power supply PCB. I myself own several of these cheap disco lights from my days from when I was starting out in DMX lighting. As you can see inside my ones, the power supply, DMX and logic board PCBs are all separate modules, so I just thought I could replace the power PCB in this broken light and it would be happy days. But as we can see in this light, the power supply and control board is one and the same. So now that I've removed the PCB, we can see this unused 12-volt header, presumably for a cooling fan that wasn't needed or omitted due to budget constraints. What I'm going to do next is plug the LEDs back into the logic board. I'm going to plug this JST connector into the unused fan output, which is just in parallel with the output of the power supply. Then I'm going to attach this to a battery pack. And we see that the PARcan powers up and enters a color chase sequence, presumably the last chase sequence that was selected by the user. So this confirms that it's the power supply at fault and not the logic board. If we look at this other PARcan that I own, you'll see that on the back I've replaced the mains inlet with a 12-volt DC jack. This is because the power supply in this went Kablammo a few days after I started using it, so I lopped it out and opted to run it off a repurposed 12-volt broadband router power supply instead. This would definitely be possible with this PCB. Theoretically, I could power the light with a 12-volt adapter via the JST connector, but I'd like to have a go at repairing it in its original format. So to start with the multimeter on continuity, I'm going to test the inrush fusible resistor. It's open circuit, hardly surprising. Next, I'm going to test the bridge rectifier. I've had a few cheap LED items fail over the years, and it's usually the bridge rectifier that's failed, and it usually fails short circuit. Not this time, apparently. Nope, electrolytic's not shorted. Doesn't mean it's okay, but... Next thing I'm going to check is the output rectifier. So what I'm looking for here is a dead short circuit. (155) that direction. It's not a normal diode drop. Normal would be 600 or 700 on the meter, so I'm guessing that's a Schottky diode. It conducts in one direction and not the other, so it appears to behave normally. So my next suspect is the switching IC. So those two pins, 3 and 6, appear to be shorted. Again, I've usually found switch mode chips tend to fail short circuit. Now that the chip is desoldered, I can check it out of circuit. I'm not sure about this. Unfortunately, the IC has no model number on it, so I'm going to have to reverse engineer the circuit to get a better understanding. The transformer I've tested, by the way, so in all likelihood it is the switching IC that's failed. So this probably isn't 100% accurate, and I've only shown the mains side of things because that's where I suspect the problem lies. But it should be good enough to get the job done. I've had to desolder one of the caps to study the board a bit better. If indeed it's the IC that's failed, I'd probably still want to replace that capacitor anyway, just as a matter of course. So, the 240-volt AC mains enters this bridge rectifier via the 1 ohm blown fusible resistor. This converts it to DC, and then it gets smoothed via the 10 microfarad capacitor. This 3.3 megohm resistor acts as a bootstrap power supply to the chip. This provides an initial startup supply before the chip self-powers via the transformer windings. The high voltage smooth DC feeds into one leg of the transformer primary. The other leg of the transformer primary connects into pins 7 and 8 of the switching IC. There's resistors, a capacitor, and a diode forming a snubber network. Again, these components all measure okay. There appears to be two 2-ohm resistors connected across pins 6 and 3 of the chip, acting as a current sense network. This is the part I've probably not understood 100%, but there's an optocoupler connected to pin 5 of the IC and the auxiliary or feedback winding, which in turn connects to pin 2 via a diode and a capacitor, which forms a basic power supply. In order to kickstart the process of the feedback winding powering the chip, this is what requires the 3.3 megohm resistor I mentioned before. Pin 3 of the chip is connected to the negative supply rail. As I said before, there are no markings telling me what make or model of IC this is. Fortunately, I found this website that allows me to find matching compatible ICs by selecting the pins based on what I've mapped them on the schematic to. For example, I know that ground is pin 3, feedback is pin 5, the drain is pins 7 and 8. Command click on a Macintosh, and click the magic button. It's found 5 compatible ICs. I then looked through the data sheets of each chip to make sure it was truly compatible on things like supply voltage and drain current, while comparing their price and availability on CPC, Rapid Electronics, and eBay. I won't bore you with me looking at all the options, but I've settled on the THX203H, which, by amazing coincidence, was hiding in plain sight in a Big Clive video where he tore down an LED power supply. A curious quirk about this chip is that it lists a ceramic timing capacitor on pin 4 for frequency modulation, which is absent from the disco light on repair. I don't know if this is optional, i.e. the chip would function without it but can be tuned with it, or if it's vital to the chip's normal operation. The Chinese datasheet bound through a translation engine wasn't helpful in this matter. So I've found, ordered, and taken delivery of the chip. Well, 10 actually. Due to component shortages, I've not found a 1 ohm 1 watt fusible resistor. But I did find a 2.2 ohm 1 watt one, which should be close enough. I have a Panasonic capacitor in stock of the correct value. What's next? You might not know this, but I'm utterly terrified of stuff going kablammo. Always have been. It might be an Aspie thing, I don't know. I went onto the EEV blog forum to ask advice. I set out what I've basically told you in this video, what I suspect is wrong, provided a schematic, and asked advice, particularly about the pin 4 capacitor issue, and how I should test it. As I don't own a Variac, I asked should I use a higher value inrush resistor, should I run it from my 110 volt transformer, should I run the disco light in series with a filament lamp, etc, etc. As of the 27th of March 2022, I've had no replies. I am on my own. So I'm pretty much ready to test it now. Normally, I'd enclose the thing on test, i.e. the power supply PCB, in what I call a Kablammo box. This is just to shield me from a potential explosion, but the PARcan case itself should make an ample Kablammo box. I don't know if this will make a difference, but I'll be powering it from a 110 volt shaver socket, which I'll show you in B-roll. So here's the 110 volt shaver socket at the opposite end of the attic where my workbench is. Actually, it spits out 130 volts, but more importantly, it's a galvanically isolated supply that gives me an excuse not to be beside the PARcan when it potentially goes kablammo. I'm shit scared right now. Well, the power is on and it hasn't gone kablammo. If I was hooked up to a heart monitor right now, you'd be forgiven for thinking it was listening to happy hardcore. Anyway. It appears that the power is functioning. I should probably try it on 240 volts. So, reassemble, rinse and repeat with the other PARcan. Hello, me again. I've just realised I've forgotten to review the pin 4 capacitor thing. I ended up not connecting a capacitor between pin 4 of the IC and the system ground or neutral, so it does indeed appear that it's an option but not a requirement of the IC. However, I have no way of knowing what specific differences there may be, if any, without further in-depth tests. I still haven't had a response to my EEV blog post. Ah well, back to me. So as you can see, that's both PARcans repaired. All in, they probably weren't worth my time. It would probably have been cheaper ordering new from an online seller, but I do want to continue learning about electronics, and I hate seeing stuff go to landfill when it can be repaired. If you enjoyed this project, please consider giving it a like and a share, and subscribe if you haven't already. And until next time, thanks for watching.